Welcome to this lecture on the alkylation of terminal alkynes. In organic chemistry, one of the most exciting challenges is figuring out how to build large, complex molecules from smaller, simpler ones. Today, we are going to explore a powerful technique that allows us to stitch carbon chains together. By the end of this session, you will understand exactly how chemists construct these molecular frameworks from scratch. To start our journey, let us think about building a toy train track to understand how molecules grow. Imagine you have a short piece of track with a special connector at the very end. To make the track longer, you first need to remove a protective cap to expose the sticky, reactive connector. Once that sticky end is exposed, you can snap on a brand new piece of track to extend the line. This process of snapping on new carbon pieces to make a longer chain is called alkylation. It is exactly like playing with molecular Lego, allowing chemists to build larger, more complex structures from smaller starting materials. Now that we understand the general idea of alkylation, let us look at the specific molecules we will be using. We are focusing on terminal alkynes. A terminal alkyne is a hydrocarbon with a carbon-carbon triple bond at the very end of the chain. This means one of the triple bonded carbons is attached directly to a hydrogen atom. Because the carbon atom in the triple bond is sp hybridized, it holds its electrons very close to the nucleus. This unique electron distribution makes that attached hydrogen unusually acidic for a standard hydrocarbon. This acidity is the crucial feature that makes the entire alkylation process possible. Building on that concept of acidity, let us visualize the overall process before we dive into the math. The diagram on your screen illustrates the two distinct phases of the alkylation reaction. In the first step at the top, labeled deprotonation, we see a strong base attacking the terminal alkyne to remove that acidic hydrogen we just discussed. The red arrows show the movement of electrons, resulting in a negatively charged acetylide ion. In the second step at the bottom, labeled nucleophilic substitution, this newly formed reactive ion attacks an alkyl halide. The arrows show the carbon-carbon bond forming while the halogen is pushed away, successfully extending our carbon skeleton. Having seen the visual overview, let us examine the mathematical and chemical representation of the first step. This formula shows the acid-base reaction where we prepare our reactive nucleophile. Conceptually, we are removing the protective cap from our train track. In this equation, R represents any generic carbon chain attached to the triple bond. The compound sodium amide acts as the extremely strong base required for this reaction. It pulls the hydrogen atom off the terminal carbon, leaving behind a lone pair of electrons. This creates the acetylide ion, denoted by the negative charge, while the sodium ion sits nearby as a spectator. The byproduct is ammonia gas, which simply bubbles away. Now that we have our reactive acetylide ion, let us look at the formula for the second step, where the actual chain extension happens. Conceptually, this is where we snap the new piece of track into place. Here, the symbol R' represents a new, different carbon chain, and X represents a halogen atom, like bromine or iodine. The negatively charged acetylide ion acts as a nucleophile, meaning it aggressively seeks out the slightly positive carbon atom attached to the halogen. It crashes into that carbon and forms a brand new carbon-carbon bond. Simultaneously, the halogen atom is pushed off, taking its electrons to become a halide ion. If the physical size of the R' group increases, this reaction slows down due to blocking. Before we move on to more complex ideas, let us see this with a concrete example. Let us look at a practical scenario where we want to synthesize 2-pentyne starting from propyne. Propyne is a 3-carbon chain with a triple bond at the end, making it a terminal alkyne. Our goal is to turn it into a 5-carbon chain with the triple bond in the middle. To do this, we need to attach a 2-carbon piece, which we can get from an alkyl halide like bromoethane. In this first step shown on screen, we mix propyne with sodium amide. The strong base removes the acidic hydrogen, leaving behind a negatively charged propanide ion, ready for the next phase. Continuing with our synthesis, we now have a highly reactive nucleophile ready to attack. We introduce bromoethane, which contains the 2-carbon ethyl group we need. The negatively charged carbon of the propanide ion attacks the carbon attached to the bromine atom. Because of this attack, the bromine atom is kicked out as a bromide ion. A new carbon-carbon bond is formed exactly where the bromine used to be. The final result, shown in the equation, is 2-pentene, a 5-carbon internal alkyne. We have successfully completed our molecular construction, physically extending the carbon chain exactly as we planned. Now that we have successfully built a molecule, we must discuss a critical limitation of this process. What happens if we try to attach a very bulky, highly branched carbon group to our alkyne? Alkylation works beautifully with unhindered primary alkyl halides, but tertiary alkyl halides present a major problem. A tertiary halide has a central carbon attached to 3 other bulky groups. When the acetylide ion tries to attack, it faces severe physical crowding, known as steric hindrance. The nucleophile simply cannot reach the central carbon to perform the substitution. This physical barrier changes the outcome of the reaction entirely, leading to a completely different chemical pathway. Let us examine this limitation with a specific example. Suppose we react the simplest acetylide ion, formed from acetylene, with tert-butyl bromide. Tert-butyl bromide is a tertiary alkyl halide, meaning the carbon attached to the bromine is also attached to 3 other bulky methyl groups. We might hope to form a new carbon-carbon bond, but as we just learned, the physical crowding prevents this. The acetylide ion simply cannot reach the central carbon to perform the substitution. Because it cannot act as a nucleophile, the acetylide ion is forced to act purely as a base, stealing a hydrogen atom from the outer edges of the molecule instead. Following up on that blocked attack, let us see the final chemical result. Instead of substituting, the acetylide ion steals a hydrogen atom from one of the outer methyl groups. When a strong base encounters a tertiary alkyl halide, the steric hindrance and high susceptibility to E2 elimination pathways dominate. This leads to the formation of an alkene rather than the substitution product. The acetylide ion turns back into ordinary acetylene gas. Meanwhile, the tert-butyl bromide collapses into isobutylene, which is an alkene with a double bond, releasing a bromide ion. This teaches us a critical rule. Tertiary halides completely fail at alkylation and undergo elimination instead. Having seen both the successes and limitations of this reaction, let us zoom out and look at why this matters in the real world. The ability to form new carbon-carbon bonds is considered the holy grail of organic chemistry. Most basic chemical reactions only change the functional groups on the outside of a molecule without altering its core skeleton. Alkylation of terminal alkynes is one of the few simple ways to actually stitch 2 carbon chains together, building a larger skeleton from scratch. This technique is heavily used in the pharmaceutical industry to construct complex drug molecules from cheap petrochemicals. For example, synthesizing synthetic hormones relies on this exact chemistry to attach specific carbon groups to steroid rings. To wrap up our lecture, let us review the key takeaways from today's topic. Alkylation of terminal alkynes is a powerful 2-step method for extending carbon chains. First, it requires a strong base to remove the terminal hydrogen, creating a highly reactive acetylide ion. Second, this ion attacks an unhindered primary alkyl halide to form a new carbon-carbon bond via substitution. Remember that you must carefully choose your alkyl halide because bulky tertiary halides will undergo elimination instead of the desired substitution. Mastering this reaction provides you with a fundamental tool for building complex organic molecules, setting the foundation for advanced chemical synthesis.